The other nice thing about the process that we call logarithmic differentiation is that it allows us to address a couple more derivatives that we might not have been able to otherwise handle. For example, consider the function y equals x raised to the 2x power. Yes, we can do that, right? We can take a variable and raise it to another variable power. What do we do with that? Well, in this case, we're going to use our logarithmic differentiation. And the process of logarithmic differentiation goes like this. We start by taking the natural logarithm of the quantities on both sides. So we take the natural logarithm of y and set it equal to the natural logarithm of x raised to the 2x power. Now we have a property that allows us to rewrite this expression on the right because the natural logarithm of x raised to a power is the same thing as that power times the logarithm of the argument. So it's 2x times the natural logarithm of x. And if I wanted to now, I could take my derivative of both sides of this equation directly. So I take my derivative with respect to x of the natural logarithm of y. And of course, that's equal to the derivative with respect to x of our product this time, 2x times the natural logarithm of x. So let's bring this over here. What happens? On the left-hand side, the derivative of the natural logarithm of y will be the same thing as y prime divided by y. And on the right-hand side, by our product rule, we're going to take the derivative of the first function, which is 2, times the natural logarithm of x, which is the second function, and add that to 2x, which is the derivative of our first function, times 1 over x, the derivative of the natural logarithm of x. Well, we can simplify this one a little bit too. Y prime will equal y times 2 times the natural logarithm of x plus, well, if I take 2x and multiply it by 1 over x, I just get 2. Now, here's an interesting thing. 2 is a common factor here inside this parentheses, and y, remember, was defined initially as x raised to the 2x power. So y prime, our actual derivative in simplified form, could be written as 2, factored out from the parenthesis right here, times y, which we'll now express as x to the 2x power, times the quantity natural logarithm of x plus 1. That is some kind of derivative, huh? Well, let's try it with another one. It looks kind of challenging as well. But, well, actually, this should look familiar to you in a way. We've got y is equal to 1 plus 1 over x to the power x. This is something we found a limit of at one point, if you recall, but we could talk about that limit. Let's try this derivative right here. Let's see what's going to happen. We're going to take the natural logarithm of y and set it equal to the natural logarithm of our quantity, 1 plus 1 over x to the x power. So what can we do? Well, by our power property, easy to say, natural logarithm of y will equal to x times the natural logarithm of our quantity, 1 plus 1 over x. Well, 1 plus 1 over x can actually be simplified a little bit here too. I'm going to take an extra added step. Natural log of 1 plus 1 over x is really the same thing. Let me just kind of do this off to the side. 1 plus 1 over x is really the same thing as saying x over x plus 1 over x, right? Well, that's just x plus 1 over x. So you're wondering, well, how does that help me, Professor Peoples? In this case, I'm going to rewrite this. I'm going to say, well, this is the natural logarithm of y will equal x times the natural logarithm of this fraction that I've got now, x plus 1 over x. And I rewrote it so that I could take advantage of my properties of logarithms, which states that x will be multiplied by the natural logarithm of x plus 1 from the numerator minus, and distributing my x, times the natural logarithm of the denominator x. So now we take the derivative on both sides. So we're going to be taking the derivative with respect to x of the natural logarithm of y and set that equal to the derivative of, we're going to have two product rules, but that's okay, x times the natural logarithm of the quantity x plus 1 minus the derivative with respect to x of x times the natural log of x. All right, how will that come out? Well, on the left, we're going to get y prime divided by y. On the right, we're going to have our product rule. So we're going to take x, we're going to take the derivative of our first function here. So we're going to take the derivative of x, which is 1, times the natural logarithm of the quantity x plus 1. And we're going to add to that x times the derivative of x plus 1 over x plus 1. We're going to subtract away from that this second piece, right? So that was the derivative of this first piece. Now we'll go to the second piece. By the product rule, it'll be the derivative of x, which is 1, times the natural logarithm of x, plus x, the first function, times the derivative of the second, which is 1 over x. So here's what we have so far. Y prime is equal to to y, times all of this. Natural logarithm of x plus 1 plus x over x plus 1 minus the quantity, well, x and x, those cancel out, right? Minus the quantity natural log of x plus 1. So let me simplify this one more time. I'm going to replace y, so this is all in terms of x. Y prime will be equal to the quantity 1 plus 1 over x raised to the x power times the natural logarithm of the quantity x plus 1 plus x divided by x plus 1 minus the natural logarithm of x minus 1. And that's about all I'm going to do to simplify this out. I would count that as 1 for my derivative. Good luck on your homework.